So in this video we are going to talk about the question in thermal and statistical mechanics which appeared in GATE 2008 examination. So let's continue with first problem. The statement is the thermodynamic variables of a system can be volume V, pressure P, temperature T, number of particles N, internal energy E and chemical potential mu. For a system to be specified by microcanonical, canonical and grand canonical ensemble, the parameters required for specific ensemble are. Okay, so let's try to understand that what kind of variable they are held constant in these three different kinds of ensembles. So in microcanonical ensemble, the total number of particles, that is constant. Okay, it's constant, and also the volume, it's also considered to be a constant quantity, and energy is also considered, energy of a system, it's also considered to be a constant quantity. Okay, so in principle what we do is in microcanonical ensemble we consider a small range of energy E to E plus dE, and then we try to evaluate the corresponding number of accessible microstates to a system in that particular energy range. But the total energy of the system, that stays constant in the microcanonical ensemble formulation. So therefore the microcanonical ensemble formulation, it's described by N, V and E. Okay, now coming to the canonical ensemble formulation. In canonical ensemble, we argue that the two parameters, that is N, the total number of particles, and V, they are in principle they are kept at constant. That's constant. But when it comes to energy, because it's not the argument that's made in the canonical ensemble formulation is that sometimes it's not possible to determine the energy of the system. Okay, so it's a variable in the canonical ensemble formulation. It's a variable, whereas the another parameter that's connected with the energy, that's the temperature, and that's easily measurable. So this is held constant. Okay, so therefore in canonical ensemble, the parameter of interest, or it's described by N, V and T. Okay, so now coming to the grand canonical ensemble, that's GCE. So here it's not only the energy which is the variable energy, it's a variable as in the canonical ensemble formulation, but also the number of particles, they are also considered to be variable. Okay, but the description of the grand canonical ensemble, it's carried out by three other parameters, which are one is the total volume of the system, okay, and then the temperature of the system, and the another quantity is that we call that as the fugacity, and denoted by Z. Z is in principle, it's connected with the another quantity of interest, that's the chemical potential Z, that is equal to exponential minus alpha, and that is equal to exponential mu by kT, where mu is the chemical potential. So therefore in grand canonical ensemble formulation, the description is carried out by making use of the volume, temperature and chemical potential. So therefore option B is the correct one here. So let's continue with next problem. The statement is the pressure versus temperature diagram of a given system at certain low temperature range is found to be parallel to the temperature axis in the liquid to solid transition region. The change in specific volume remains constant in this region. The conclusion one can get from the above is. Okay, so let's try to understand with the help of diagram here. It's a pressure versus temperature diagram, that's a phase diagram. Okay, it's a pressure versus T diagram, and it's given that it's a constant in a certain liquid to solid transition. So liquid to solid transition. Okay, so if it's a constant, so let's see how we can understand it with the help of a Clausius-Clapeyron equation. Okay, so from the Clausius-Clapeyron equation we can correlate dP upon dt that is equal to L by T delta V. Okay, so now it's given that when this liquid to solid transition is taking place, dP is equal to 0. Okay, it's given that dP that's equal to 0, so this implies dP by dt that is equal to 0, and that is equal to L by T delta V. Okay, so it's also given that during this transition the specific the change in the specific volume that remains constant, and that change is delta V, and it's given that it remains constant during this transition. Okay, so that means that is equal to delta S upon delta V, and that is equal to, we are saying that is equal to 0 because delta P is equal to 0. So that means delta S that is equal to 0 when this liquid to solid transition is taking place. Okay, so therefore the right option here is the change in entropy is 0 in the liquid to solid transition region. Okay, so that's the correct one here. Okay, so let's quickly take a look at the other option. The entropy of solid is 0 in this temperature region, because we are not talking about only the solid, but it's a liquid to solid transition, so therefore option A is incorrect here. The entropy increases when the system goes from liquid to solid phase in this region, which is not true, as we notice that L by T delta V that is equal to 0, so therefore entropy it couldn't increase here. In the option C, the entropy decreases when the system transforms from liquid to solid phase in this temperature region, this is also not true. So D is the correct option here. Let's continue with next problem. A system containing n non-interacting localized particle of spin half and magnetic moment mu, each is kept in constant external magnetic field B and is in thermal equilibrium at temperature T. The magnetization of the system is, okay, so let's first of all try to find out the interaction energy of the spin in presence of external magnetic field. Okay, the interaction energy E of spins in external field B is given by E that is equal to minus mu dot V. So in principle what we can do is we can we have two different orientation for the spin in the presence of external field. Okay, so let's call the energy E1 that is equal to mu minus mu1 mu minus mu dot B, and that is equal to minus mu V when mu and V they are in the same direction. So that is when the magnetic moment it aligns along the field direction. Okay, so that is when mu it is parallel to V, and when it's anti-parallel the alignment, so that means mu dot B, the angle between them, that's 180 degree. So these are the two different options. Okay, so then cos pi will give us an additional -1 sign, so this will be minus mu dot V, and then when they are having anti-parallel alignments, that's when the angle between mu and V is 180 degree. So in that case the interaction energy it comes out to be equal to with positive sign, that's mu V. Okay, so that is when mu anti-parallel, it is anti-parallel to B. So therefore the partition function for a single spin is Z1 that is equal to exponential minus beta E1 plus exponential minus beta E2, and that is equal to exponential beta mu V plus exponential minus beta mu V, and that is equal to 2 cos hyperbolic mu V upon kVt, where beta is, we have used that beta that is equal to 1 by kt. Okay, so now because the spins, they are non-interacting and they are localized particles, and we can treat them as distinguishable because spins are localized, so that means we can treat them as distinguishable. So when we can treat them as distinguishable, so n spins partition function will be simply Zn, that is equal to Z1 power n, and that is equal to 2 cos hyperbolic mu b upon kt and power n. Okay, so let me call this as equation 1. Okay, now the Helmholtz energy for this system, because our ultimate aim is to look for the magnetization of the system. Okay, so let's see how we can determine the magnetization from the Helmholtz energy. Okay, so the Helmholtz energy for this system is F, that is equal to minus kVt ln Zn. So therefore, by making use of the equation 1, this turns out to be equal to minus nkt minus nkt logarithmic of 2 cos hyperbolic mu b upon kt. Okay, so let me call this as equation 2. Now we want to determine the magnetization of the system. Okay, so for that purpose I will take you back to the introduction to the thermodynamic potential, and then we will try to see how we can determine the magnetization from the Helmholtz energy. Okay, so we know that for this system du, it's the modified form of the first law of thermodynamics, du, that is equal to dq minus dw, and this can be rewritten as dq, that's tds. This is with the help of the second law of thermodynamics. Okay, so here we use ds, that is equal to dq reversible by t, so dq we can replace with tds. Okay, and then minus mdb, so that's the mdb. Basically it represents here the work done by the external magnetic field on the magnetic moment m. Okay, so therefore from here we can conclude or we can obtain the corresponding change in the Helmholtz energy for this system. So this is the modified equation for this system, for the system of magnetic moment. So let me call this equation 3. So the Helmholtz energy is defined through relation F, that is equal to U minus Ts, and from here I can define a small change in Helmholtz energy dF, that is equal to du minus Tds minus sdt. Now substitute the value of du from equation 3. Okay, so replace du with this equation, so this is equal to tds minus m dB minus tds minus sdt. So tds will cancel with tds, so we are ultimately left with df, that is equal to minus m dB minus sdt. So from here I can define the magnetic moment of the, or the, you can say the magnetization of the system m as minus df upon dB by keeping temperature constant. So now we are going to make use of relationship 4 and equation 2. So by making use of equation 2 and 4 we can determine the magnetization. So let me introduce a page here. Okay, so the magnetization, net magnetization is given as m, that is equal to minus df upon dB by keeping temperature constant, and that is equal to nkt nkbt, and then 1 upon 2 cos hyperbolic mu b upon kbt, and then again it's differential, That's 2 sine hyperbolic mu v upon kBt, and then multiply by mu upon kBt, mu upon kBt. So here we are having one negative sign here and additional one more negative sign with the value of the f here in equation 2. So this negative and negative, that will give us a positive. So that's why I haven't kept that negative sign here. Okay, so this is equal to n mu tan hyperbolic mu v upon kBt. Okay, so that's the net magnetization of the system. So let's see which option matches with the result. So therefore n mu tan hyperbolic mu v. So therefore V is the correct option here. Let's continue with the next problem. A photon gas is at thermal equilibrium at temperature T. The mean number of photons in an energy state E is equal to h cut omega is. Okay, so we know that the photons are boson basically. Okay, so hence they will follow they follow Bose-Einstein statistics. So that means the mean number of the photons, that is mean number of photons, okay, so that is the occupation index is given by, that is equal to n average, that is equal to exponential E minus mu upon kBt minus 1, because for the photons we know that for photons the chemical potential, that is equal to 0. Okay, so therefore this equation reduces to 1 upon exponential E upon kT E upon kBt minus 1, because it's given that E is equal to h cut omega, so that is 1 upon exponential h cut omega upon kBt minus 1, and in other words this can be rewritten as exponential h cut omega upon kBt minus 1 and its power minus 1. So therefore D is the correct option here. So let's continue with the next problem. The statement is, consider a system of n atoms of an ideal gas of type A at temperature T and volume B. So we are having a situation where we are having a system of n atoms. So let me draw it schematically. So we are having system A, which consists of n number of atoms at temperature T and at volume B. Okay, and it's a system of an ideal gas. Okay, so that's another point that we should note. This is ideal gas. Okay, now it is kept in diffusive contact with another system of n atoms of another ideal gas of type B. Okay, so this is in contact with the another system B, which also consists of n atoms of type B at temperature T and volume B. Okay, it's again an ideal gas. So that means both of these two systems consist of ideal gas. So once the combined system reaches the equilibrium, okay, so the entropy of the final system is the same as that of the sum of the entropy of the individual system. So that means we have to look for the entropy of the composite system. Once after the diffusion, the composite system, it comes into the equilibrium. So once the diffusion has taken place, so then we will have a situation like this. So some of the type A atoms, they will be in the they will, the atoms from both sides, they will mix with each other. So we will have a mixture of type A and type B, something like this. So A and B mixture, so with total 2n atoms and with the total volume of 2V. But now, because it's a purely ideal gas, so here the final temperature, it's not going to change in visible. So because the gases, they are ideal in nature, and their internal energy, that's a purely kinetic in nature, because gases are ideal in nature and their internal energy is purely kinetic in nature, which this internal energy, it depends only on temperature T. Okay, and here because both of the mixture, they are at the same temperature initially, because temperature of mixture A, that is equal to temperature of mixture V, and that is equal to T. So therefore final temperature will be T final will be equal to T. So that means delta T for the mixture, that is equal to 0. Okay, so that's a important conclusion, because delta T mixture is equal to 0, and the fact that the internal energy of the system of gases, that's also a temperature dependent quantity. So that means delta U equal to 0. So by applying the first law, we notice that dq, that is equal to du minus dw. So du here, it's 0, so that is equal to 0 minus p dv. Now dq, it's going to be plus dw. Okay, so let's call this as equation 1. Now the entropy change for the system is given by the entropy change for the entropy change for the composite system will be equal to entropy change for system A plus entropy change for the system B. Okay, so the net entropy change for the system is delta S system, which is the composite system, that is equal to delta S1 plus delta S2. This is the entropy change for system A, and this is the entropy change for system B. Okay, and that is equal to the heat change involved in system A, dq1 by T plus dq2 by B. Okay, and that is equal to P dB upon T for system 1 plus P upon T dB for system 2. Okay, so here we will apply the ideal gas equation, that is because it's given that both of the systems, they contain the ideal gases. So by making use of the fact that PV, that is equal to N kBT. So from here we conclude that P by T, that is equal to N kB upon B. So therefore the entropy change that is equal to n kb into dB upon B plus n kb dB upon B. Okay, so let me introduce another page here. So therefore delta S composite system, so that is equal to n kb ln final volume ln B2 upon B1, okay, for the first system, plus n kb ln B2 upon B1, it's for the second system, that's system B. Okay, now this is equal to n kb ln, it is twice the initial volume. So when there is a complete mixing of the gases in two different systems, so the final volume for the composite system will be, that is 2B, and the initial volume is V, plus n kb ln 2B upon B, that is equal to 2n kb ln 2. So that's the final answer. So let's see, so therefore we notice that it's the option B that matches with our result. So therefore option B is the correct one. So let's continue with the next problem. So the statement is, consider a system of two non-interacting classical particles. So we are given a system of n is equal to 2 non-interacting classical particles which can occupy any of the three energy levels. So this system of two particles, it can occupy any of the three energy levels with energy E that is equal to 0, E and 2E, having degeneracy of G, the G value that is given to be 1, 2 and 4. Okay, so we have to find the mean energy of the system. So that's the mean energy means that's a energy per particle, the average energy per particle. Okay, so we can work out this problem by making use of the partition function approach. So let's try to first write the partition function for this system. So so I'm writing the partition function for single particle, because we have to work out the average energy which represents the mean energy per particle. So Z1, that is equal to Gi exponential minus beta Ei, I here because we are having only 3 levels, so 1 2 3. Okay, so that is equal to, so G1 which is 1 into exponential minus beta E1 which is equal to 0, plus G2 which is 2 exponential minus beta E, plus G3 which is 4 exponential minus 2 beta E, that is equal to 1 plus 2 exponential minus beta E 4 plus 4 exponential minus 2 beta E. So that is the single particle partition function. Now the average energy per particle, that's given by the average energy per particle, now the mean energy of the system, that is equal to minus curly beta of ln Z1. So that means minus curly beta of ln 1 plus 2 exponential minus beta E plus 4 exponential minus 2 beta E. Okay, so let's move to the next page. So its differential is equal to, that is minus 1 over 1 plus 2 exponential minus beta e, 1 plus 2 exponential minus beta e plus 4 exponential minus 2 beta e, and then again its differential, so that will be 2 exponential minus beta e, and then we will have another factor of minus e because of again the differential of the exponent with respect to beta. And then the second term, for the first term we will have 0, this its differential that will give us 0, and from the last term we will have a term of 4 exponential minus 2 beta e, and then multiply by minus 2 e. So this upon solving will give us, this is equal to, we are having minus outside and again another minus, so this is equal to, and e is common in both cases, so that is equal to e into 2 exponential minus beta e plus 8 exponential minus 2 beta e upon 1 plus 2 exponential minus beta e plus 4 exponential minus 2 beta e. Okay, so let's check which option matches. So this is equal to e into 2 exponential minus beta e plus 4. Which one is having the 4? So let me check which option matches with the. So it's not the option C, but it's the option B. If you just compare the final result that we have, it's the option B here. That's the correct one, not the option. This is the correct one. Option C is not, because we are having a factor of 8 in the numerator. So here it's a factor of 8. So option B is the correct one here. So let's continue with the next problem. The statement is, two identical particles have to be distributed among 3 energy levels, and let RB, RF and RC represent the ratios of probability of finding 2 particles to that of finding 1 particle in a given energy state. The subscripts B, F and C corresponds to whether the particles are boson, fermion and classical particle respectively. The ratio RB is to RF is to RC is equal to. Okay, so let's first try to understand the distribution of particle according to their statistics. So we are having a system of 2 particles. So n is equal to 2, which are identical. Okay, and then we have to distribute these particles in 3 different energy states. Okay, 3 energy levels you can say. So let's try to write the distribution for the bosons first. Okay, so I will label these 3 states as 1, 2 and 3. It's state 2, energy state 1, 2 and 3. Okay, so similarly for the fermions we can draw the same type of picture. Again we are having 3 energy level labeled as 1, 2 and 3. Okay, and similarly for the classical particles. Okay, so we'll have 3 energy states 1, 2 and 3. Now when we treat the particles as boson, so in that case they can either stay together or alone also. So there is no occupancy constraint on the number of boson that each individual state can have. So we assume that the particles they behave like bosonic particles, so this distribution might be feasible with them. here we are having only one single boson in each individual energy state. Okay, so and the next option is both of the boson, they are in the same energy state. Okay, and then the last option. Okay, similarly, now when we talk about the fermion, they are subjected to the Pauli exclusion principle. Okay, so that means Pauli, so they are bound to satisfy the Pauli exclusion principle. So that is, we cannot put more than one fermion in a single energy state, single particle energy state. So these possibilities will be feasible. So this is the third option. But when we talk about the classical particle, where they become distinguishable. So classical particles are distinguishable basically. So when we treat them as distinguishable, so again there is no constraint on the occupancy. So let's label them as A and V, and then the other possibility is V and A. Okay, AB, B and A. AB, B and A. So then the last option is that when we have both of the particle together in the same energy state. So these are the possible distribution for the classical particle. Okay, now we have to find the ratio of the probability of finding two particles to that of finding one particle in a given energy state. So now let's continue our discussion with the boson first. Okay, so for boson, let's talk about the energy state 1. Okay, so we have to find the probability RB, that is the probability of finding two particles to that of one particle in a given energy state. So if we just talk about the energy state 1, so here out of the we are having 1 2 3 4 5 6 six possible distribution, and out of these 6 possible distribution we are having only one particular distribution where we are having two particles here. So this is this one. So therefore the probability of finding two particles in a given energy state to the probability of finding one particle, a single particle in the same energy state, that is equal to 1 out of 6 and divided by probability of finding only one particle in an energy state. So there are two such possibilities, the first one and the second one. So that is equal to 2 divided by 6, and this is equal to 1 by 2. Similarly, we will find the probability for the fermion, the ratio for the fermion RF. So again P2 upon P1, because here we cannot find the fermions together in the same single particle state. So this is P2, that is equal to 0, and then P1, that is equal to 2. Okay, 2 divided by 3. So here we are having only these two options, and then we have total options are 3, 1 2 and 3. Okay, so therefore that is equal to 0. Now for the classical particle RC, that is equal to probability of finding two particles in the same energy state, and then probability of finding one particle, and that is equal to, so let's focus on the first case. Okay, so in total we are having 1 2 3 4 5 6 7 8 9. Okay, so out of these 9, so there is only one particle distribution where we can find two particles together. Okay, so therefore P of 2, that is equal to 1 divided by 9, and P of 1 is equal to 1 2 3 4 divided by 9, and this turns out to be equal to 1 by 4. So therefore the ratio RB is equal to RF. Therefore RB is equal to RF ratio RC, that is equal to 1 by 2, 0, 1 by 4, or this can be equivalently written as 1 is to 0 is to 1 by 2. So therefore D is the correct option here. So let's continue the next problem. The statement is, consider a two-dimensional electron gas of n electrons. So we are having n electron system whose mass is m, because it's an electronic system, so it's a basically non-relativistic system. So non-relativistic system, which implies that the momentum energy relationship p square, that is equal to 2 me, that will be valid for this system. Okay, and it is confined in a system of size L by L. It's a two-dimensional system, so area of this system, that is equal to L square. The density of states between the energy range E to E plus dE. So that means we have to find the GE dE in the range E to E plus dE. So that's our objective. So we will follow the statistical approach here. So first of all, we will write the expression for the number of states with momentum less than or equal to P. Okay, so I will denote that as omega P, the way we do in statistical mechanics. So omega P, that is equal to GP basically, and that is equal to the area, the ordinary area, the area in the ordinary space, and then multiply with the area in the momentum space. Okay, so that's basically the available phase space volume, you can say. Okay, divided by the h square. Okay, that's the elementary area bounded by a one single unit cell. Okay, so that will give us the total number of states with momentum less than or equal to P. Okay, so from here what we can do is we can determine GP dP, that's the number of states with momentum P to P plus dP. So this denote the number of states from P to P plus dP. So this is this quantity, and that is equal to d of omega P divided by dP dP. Okay, and this is equal to 2 pi a P dP upon h square. So let's call this as equation 1. Now we can directly write the expression for the number of states between energy range from E to E plus D by making use of this expression, GP dP, you can say, or this is also written as omega dash P. But let's follow the same notation. So now the number of states with energy range G from E to E plus DE, that is denoted by GE dE. So that is equal to 2 pi a upon h square. Note that here a is equal to L square. Okay, so this as it is. Now I'm going to replace P dP with the appropriate expression in terms of energy. So if we just take a look at the energy expression for the non-relativistic particle, it is P square, that is equal to 2 me. Okay, so that means what I can do is I can rewrite this as 2p dP, that is equal to 2m dE. So the factor 2 will cancel with each other, so that means we are left with P dP, that is equal to m dE. Okay, so we can replace the P dP with m dE, so multiply by m dE. So that's the expression for the number of states with energy range ranging from E to E plus dE. But here we haven't yet noted that, or we haven't yet discussed that the electrons, they also have a spin degeneracy of 2. The spin degeneracy for electrons, that is denoted as GS, that is equal to 2s plus 1, where s is equal to 1 by 2. And if you substitute that, then a factor of 2, we are supposed to consider this in the density of state expression. So therefore the density of states in the range from E to E plus dE, that's given by GE dE, and that is equal to GS multiplied by this expression 2 pi A upon H square M dE. So GS is equal to 2. So when you substitute this value, so we obtain 4 pi A. Now A I am replacing A with L square. 4 pi L square M upon H square dE. So therefore we notice that option A is the correct one here. So let's continue with the next problem, which is also connected with the same statement here. So it's again the same statement as from the previous question, but now we have to find the ground state energy Eg of the system in terms of Fermi energy Ef and the number of electron. Okay, so let's see how we can do this. So first of all, we are going to determine the total number of electrons in the system in terms of the Fermi energy. Okay, so and because we are talking about the ground state energy, so that means the system will be at ground states when the corresponding temperature is absolute zero. Okay, so at absolute zero, all the energy states below the Fermi level, they are going to be occupied, whereas all the energy states above the Fermi energy, they will be empty. So the corresponding number of particle in the total number of particle in the system is given by 0 to infinity the Fermi Dirac probability distribution function Fe multiplied by GE dE. Okay, so here the Fermi Dirac probability distribution function Fe, that is equal to either 1 when energy is smaller than Ef, and this is equal to 0 when energy is greater than the Fermi energy. So all these properties, these two properties, they are valid at absolute 0. Okay, so and the another so that means here we need not to perform the integration from 0 to infinity, but it's only effective only 0 to Ef. So therefore the number of particles in the system that is given by, that is equal to 0 to Ef up to the Fermi energy, and then Fe up to Ef, it is having a value of unity, so I am replacing it with unity, and then the expression for the GEDE that we just obtained in previous problem, so that is equal to 4 pi L square M 4 pi L square M upon H square and then dE. Okay, so this is the expression for the density of states in the range E to E plus D dE, and this is equal to N, that is equal to 4 pi L square M upon H square multiplied by Ef. So let's call this as our result 1. Okay, now we will obtain the expression for the ground state energy of the system. So now ground state energy of system is given by, let's say it's E0, and that is 0 to Ef of the Fermi energy, and then this is the energy multiplied by the probability distribution function and the density of state GE dE. So you have to remember this expression for the evaluation of this quantity. Okay, so after substituting it, so see up to Ef, this is having a value of unity. Okay, so GE dE, it's known to us, so we can obtain quickly the value of E0, that is equal to 0 to Ef, okay, and then E, and then multiply by GE dE. So GE dE is equal to 4 pi L square M upon H square dE, and it comes out to be equal to 4 pi L square M upon H square multiplied by E square by 2. Okay, no, not E square but Ef square by 2. So and this is nothing but 4 pi L square M upon H square into EF multiplied by EF by 2. So if we just take a look at the first expression here, this is nothing but N. So that means the ground state energy of this two-dimensional system, that is equal to N EF divided by 2. Okay, so therefore B is the correct option here.